Okay, so now that we understand the recursive structure of edit distance, and in particular after we saw the example, it's straightforward to get a dynamic programming algorithm for edit distance. But before I'm doing that, let me maybe go over what we really get with the input. I should have said it earlier, but I didn't. So as part of the input, we get a cost model. What is the cost model? We have an alphabet, sigma, as we encountered before in this course, and we have a cost function, right? Essentially, we have a table that for every 2 characters tell us the cost of aligning one character against the other, okay? And in particular, implicitly in all the discussion we are doing here, although it's really not required formally, but that's the intuition, we are assuming that the diagonal matching character to itself costs 0. But let me emphasize that the algorithm works even if it wasn't true. And in addition, we have this cost delta, which is the cost of inserting and deleting a character, which again, in the most general problem, you can define delta to be different to different characters and so on. Let's not go down this black hole. So now the cost is hopefully clear how we get it. And now here is the resulting recursive program for this problem using explicit memoization, right? So the input is into strings, A and B, edit distance, allocate an array of size m by n, or m plus 1 by n plus 1 if you want to formalize, fill all the entries by an invalid value like infinity, and then it calls on the inner edit distance function. And the inner distance function just do the obvious thing. It checks whether, so the recursive call is on I and j, right? The prefix of the first I character of the first string and the prefix of the first j character of the second string, and it computes the minimum edit distance of those 2 prefixes. So it checks if this value is already stored in the table, it just returns it immediately. If it's a boundary case, I equals 0, j equals 0, it just fills the value directly, right? Which, if you think about it for a second, is I plus j plus delta, right? If I is 0, it's j plus delta. If j is 0, it's I times delta. So that's correct, and return it. Otherwise, we have to go through the 3 possibilities, right? Either insert a character or delete a character. And the third option is aligning the 2 characters. And if we align the 2 characters, we have to see the cost of aligning the AI against BJ. So we look up in this cost table that we have, and we call recursively on I minus 1, j minus 1. And then we just we compute the minimum of those 3 options. This is the solution. We store it in the table and we return it. Okay, so this is simple enough. And if you think about this for a little bit, we are interested, of course, in edit distance of mn. So it's easy to see that there are m plus 1 times n plus 1 distinct recursive calls. Every recursive call costs constant time. So overall, this is going to be O of mn. Okay? Good. Okay, now turning this into a dynamic program is very easy because we already saw in the example that really what we have to do is to fill the table row by row or column by column. It doesn't really matter. So if you do that, you initialize the table, right? You allocate the table, you initialize the first row and the first column, and then you go row by row, and every row you fill it from left to right, and you just use the recursion. You check for the 3 possibilities and you return the minimum. The important thing here is, as before, that the cell ij only looks on the 3 cell adjacent to it, to its left and above it, right? You need to know those values before you can compute this value, right? And that's all we are using here. So that's why we can do it either row by row or column by column. It's kind of oblivious. As long as you're guaranteeing it at any point in time, the 3 cells, their value is computed. As for the running time, it's mn because that's the number of times the inner loop is going to be performed, m times n. And the space is, of course, m times n because that's what we allocate for the table m. So this is it. Next, we will see how to improve the space.